Alright, so we have cleaned up our data and we have grouped them by the treatment. So we got rid of some stuff which we do not need, and right now we have only the things that we need to plot the graph or do the statistical analysis. So moving on, we're going to start off with the statistical analysis. We're going to do two things. First, we're going to check for normal distribution in the data, and the second thing that we're going to do, we're going to be doing one analysis of variance along with a post hoc test. So first we're going to start off with the normality check. So I'm going to put in a comment over here. I'm going to say statistical analysis, and in brackets I'm going to write normality check. So for normality check, there can be a lot of tests. The one that we're going to be using is Shapiro-Wilk test. So since we have three data points for every data set, we're going to be using this Shapiro-Wilk test because it is good for when you have less data points. So we're going to start off with the data set that we made during the cleaning, but not the whole thing. I want up till this much. I don't want the longer version of the data because when I'm going to be doing the Shapiro-Wilk test, it's going to compare the groups like according to one column. Like it will make the test depending on each column. So I want the column data, not I want the longer form of data where I have the separated columns. So I'm going to copy till here, and after this, if I hit Command Enter, so you can see FC1, FC2, FC3. Now if I do a Shapiro-Wilk test on this, what it's going to do, it's going to put the test on FC1, FC2 and FC3, but that is not relevant to us. We want to have the test done on the data points of a particular treatment. So for control, we want whether the data is normally distributed or not. And when we do a normality check, if we have same data points, same values, we cannot check normality for that. And since in PCR, when we do a fold change, the control always comes to 1. The fold change of the control always comes to 1. So we're going to omit this group while we do the Shapiro-Wilk test. But the rest of the groups, we have different values we can check for normality. So I want to check whether GLC has the data points which are normally distributed in, comparing all these three. So I want a comparison like this. But Shapiro-Wilk test does it on the basis of the column. It does not do it on the basis of the row. So what I would do, I would want to change the rows into columns and the columns into rows. So what I will do, I will change. I want to get all of these transposed over here, and all of these values transport on the top. So I want to make a 90-degree turn of the table. So basically I want to transpose the table. To do that, I'm going to pipe this into a very simple function called T, or transpose, and that's going to do the trick. So now you can see you have control GLC, LXI4 and G plus L on top, and the values of those corresponding to the columns under those treatments. But over here, the major problem that will happen is when I'm going to do, let's say if I do a Shapiro-Wilk test on this, it will consider this also as a value, and it will say that this is not a numeric value, so we cannot do a Shapiro-Wilk test on this. Actually, what has happened when we transpose the data, this column was this control GHC, the treatment column was put onto the top. This also became a value for the first row. So right now the headers of the columns are 1, 2, 3 and 4, whereas the value starts from control GLC, LXA4 and G plus L. So these are also one values of each of the column. And we need to put these as the headers, these 4 as the headers, and the rest of the values remains the same. So to do that, first, this is a table. Okay, this is a matrix. This is a table. This is not a data set. First, we need to convert this table into a data set. So to do that, we're going to pipe this into another function, and we're going to say as.data.frame. All right. So if we do this, then you can see the square bracket 1, 2, 3, and 4. It is converted to V1, V2, V3, V4. So now, since that change is done, I know that this is a data frame. Otherwise, they would have thrown an error saying the values cannot be turned into a data frame. All right, so one part of the work is done. We have converted the table into data frame. Now we can manipulate that. What we want to do is put the first row as the names of the 4 different columns. So I'm going to pipe this again into another set names. So we already did a set name on top over here, where we specify the names of the columns. Right now, we are not going to specify the names of the columns. We're just going to say dot and 1 dot comma. So what this does is it takes the data frame that is there, takes the data frame that is on the left of the pipe, and puts it saying that put the values of the first row till the last row as the names of the column. Set the names as the first row, from the first row to the names of the column. If we do this, now you can see you have those V1, V2, V3, V4 removed, and you have control GLC, LXA4 and G plus L. So it took these names and it replaced the V1, V2, V3, V4 with these 4 names. But again, we have a problem. Still, this is there as a value. We need to remove that. To do that, we're going to again pipe this into a function called slice, and slice will say remove the first row. So if we do this, now you can see first row has been removed and we have our columns separated with the names as control GLC, LXA4 and G plus L. Next, what we need to do, since we converted the table into data frame and we manipulated the data frame, right now all of these are not numerical values, and to do a Shapiro-Wilk test we need to convert all of them into numeric values. So I'm again going to pipe this, and I'm going to use the mutate function, but this time I'm going to mutate all. I'm going to say as dot numeric. So once I hit enter on this, let's remove the pipe. Once I hit enter on this, you're going to see the zeros at the back of every value in control. They're going to disappear and 1 is going to shift to the right. All right, so command enter, and you can see the zeros have disappeared and these have been converted into numeric values. Now we can go for the Shapiro-Wilk test. So again, I'm going to pipe this into a function called summarize. So if you are doing a Shapiro-Wilk test, you can do separately for each of the column. But what I want is I want one table with the values of the Shapiro-Wilk test of the different columns. I just want one table. I don't want them separately. And like I said, we won't be doing it for the first column, that is the control column. We're going to be doing it from 2 to 4. So Shapiro-Wilk test, we're going to say Shapiro.test, and we're going to specify the name of the column. So first column is GLC, and we want the p-value. All right, so Shapiro-Wilk test, how does it work? If your data is normally distributed, the p-value should be more than that of the alpha level, that is more than 0.05. If it is less than 0.05, that means your data is not normally distributed and you need to resort to a non-parametric form of statistical analysis. We need the p-value for that. So to get the p-value, we'll give a $ and we'll write p dot value. This for the first, this for the second column, GLC column. I'm going to do it similarly. I'm going to just copy this. Change this to LXA4. And again, I'm going to copy this and change this to G plus L. Now, if we hit Command Enter, summary, expected symbol. All right, I need to give commas after each of them. Comma, comma. All right, now if I do it, again, it's throwing me an error. It's saying caused by error object G not found. All right, so over here in the last one, you can see the plus symbol highlighted in pink. And that means it is separating the G from L by a plus. It is not considering this as one value. So in order to do that, what we need to do, if we have special characters in our column names, we do it like this. I'll get rid of this. And we need to put the G plus L, I mean the name that is having the special character, inside a backtick. So the backtick is like this. It's above the tab button on your keyboard in Mac. I think it's similar in Windows, and it's just left to the numeric 1 button on top. So over here, if I write G plus L, then you get then you get it completely in white, and you don't have the plus symbol highlighted in pink, and you know that it is all right. We hit Command Enter after this. Over here, you can have the p-values. You can see the p-values of each of the group. Now to simplify this more, I'm going to write GLC equals LXA4 equals. I'm just putting all the values so that this whole thing does not comes in. I'm putting all the 3 different values inside inside a variable, so that instead of that it will show the variable. So GL, anything you can give it. So again, if I have to give a plus over here, I have to put it inside backticks. So G plus L. After this, if I run it, you can see GLC, LXA4, and G plus L. And all of these are having p-values way above 0.05, so we can consider them to be normally distributed. So we can go for a parametric test, and the parametric test that we're going to do is ANOVA. And for multiple comparisons, we're going to be doing post hoc test. So let's get started. Again, I'm going to be giving a comment, statistical analysis. And this time, inside the brackets, I'm going to write ANOVA and 2 keys post hoc. So why do we do a post hoc? We do a post hoc since we're doing ANOVA. ANOVA will give you an overall significance. It will not give you the exact significance between the groups. It won't compare the groups specifically. It won't give you that significance level. So for that, for multiple comparisons, and to get the exact p-value between two or more groups, we do a post hoc analysis, which will give you that exact p-value. For ANOVA is very straightforward. What you can do is you can again write the ATP 6. Right? Did we change this? No. Okay. So this whole thing, I want to use this whole thing, but I don't want to write all of these codes again and again. So what I'm going to do, I'm going to put it into a variable so that I can use this variable anytime I want. So I'm going to select this whole thing. So now we put it into a variable, new variable, and if we use the variable unless we execute it, the next code won't know that it is under a variable. So we need to execute it once. Now we have this ATP containing this whole thing, so we can use this ATP. We don't need to write the whole thing. So we pipe it into a function called analysis of variance, AOV, and this works a little bit different. The data or the data frame, it comes at the end. It does not come at the beginning. So the first thing that comes is the formula, that is with respect to what we want to calculate the ANOVA. We want to calculate the variance. So we want to calculate the variance of the fold change group, fold underscore change, because that was the group that we named over here, fold change. So fold change with respect to the treatment column, right? Because we have grouped it with respect to the treatment column. So to say that, we're going to give a tilde sign. So we did a backtick. It is shift that button and it will give you the tilde. It's right next to the numeric 1 button on top. So we'll write treatment and we'll give a comma, and we have to specify the data set at the end. So we'll write data equals dot. So the dot signifies that whatever is coming before the pipe, pull it and put it over here. So we don't have to write the name of the data set here. We're going to pipe this into a summary, this summary function, and it's going to give us the overall significance. That is, it's 2-star significant, which means it is the overall significance of the test is the p-value is less than 0.01. That is why it is 2-star. Like I said, it won't give you the multiple comparisons. For that, we need to do post hoc analysis, and we're going to write ATP, or we can copy this whole thing to here, and we're going to pipe this into something called Tukey HSD. So once we do that, it is going to give us the Tukey's post hoc test, and you can see you have the p-values corresponding to the comparisons of two groups. So all the groups are compared. For the first one, you can see it's between control and 40 millimoles of glucose. Don't worry about the /n, it will go when we make the graph, like I said. So this one has a p-value of 0.001. So this is less than 0.01, right? We got 0.001. All right, 2-star. Okay, so p-value is less than or equal to 0.001. So this is the value by why we got the p-value, overall p-value, to be 2-star, right? All right, so that's how you do a post hoc test with the analysis of variance, and you can get this p-value for the multiple comparisons between the groups. All right, so that's it for the statistical analysis. In the next video, we are going to start getting our hands dirty by putting some codes that will make the graph, the bar graph, and we're also going to put the data points of the bar graph, the lines that corresponds to the significance values. We're going to put the significance values as well as the stars. And we're going to make the graph look pretty so that it is ready to go for a publication. We can put that into an article, or put it into publication. All right, so that's it for this video. I'm going to see you in the next one. Bye bye.